G'day viewers, in this episode we're going to disprove the standard model of particle physics premise that the value of the neutron mean squared charge radius is driven by complex Quark-Gluon dynamics, which forces it to take a negative squared value. We are going to show by referring to episode 5 on this channel how we derived an experimentally verified exact analytical solution for the neutron mean squared charge radius, which does not need to be expressed as a negative squared quantity. That is to say, it can be expressed as a negative squared quantity if you wish, but it does not need to be. It can be expressed as a positive quantity instead, which is a more natural and intuitive way for people to think. This means that the standard model of particle physics premise of complex Quark-Gluon dynamics leading to a negative squared charge radius is just speculative guesswork. The standard model of particle physics has no idea if its premise is actually correct or not. The important message that I'm delivering here is that even at the elite level of physics, people will follow each other like sheep, simply to avoid becoming professional outcasts. Accepting a premise such as complex Quark-Gluon dynamics lead to a negative value for the neutron squared charge radius without contesting the said premise is not very much different from the flat earth days. Many people will seem to agree to anything that someone more senior might say. We have a word for this. It's called intimidation. This video provides a brief overview of episode 5, and I strongly urge all viewers to watch it for the complete solution pathway. Okay, so what's the bottom line? Well, we show that the negative dimension derived by the standard model of particle physics describing the size of a neutron can be expressed as a positive dimension with precisely the same mathematical form as the proton. This is a very important fact, so please try and keep it in mind. That is, our exact solutions for the size of the proton and neutron have precisely the same mathematical forms. Okay, assuming you have watched episode 5, let's compare our exact analytical solutions to 3 key authoritative sources. That is, the 2001 Selleck's collaboration experiment, the 2002 Kamenov result, and the 1995 Kopecky result. The first set of comparisons to authoritative sources we shall make involves 2 of them. That is, the Selleck's collaboration measurement of the proton root mean squared charge radius in 2001 and the neutron mean squared charge radius measured in 1995 by Kopecky and utilised in 2002 by Kamenov. The reason the Kamenov value was utilised is because of the revised experimental tolerance compared to the original 1995 Kopecky research. The Kamenov conclusion is slightly more uncertain, making it a marginally better baseline to utilise as an authoritative comparison because it's a more recent estimate. First up, let's compare our 0-point field equilibrium radius for the proton to its root mean squared charge radius as physically measured by the Selleck's collaboration. As we can see, the correlation to experimental observation is astonishing. Thus, we have experimentally validated our solution with respect to the proton. Next, let's compare our solution to the experimentally validated mean squared charge radius of the neutron. Once again, we see an astonishing correlation of our 0-point field equilibrium radius to experimental observation. Thus, we have experimentally validated our solution with respect to the neutron as well. However, on screen inside the green box, you will see an extract taken from Sparveris, which describes how the neutron mean squared charge radius manifests as a negative quantity. Sparveris writes that, quote, "The neutron is a cornerstone in our depiction of the visible universe. Despite the neutron's zero net electric charge, the asymmetric distribution of the positively and negatively charged quarks, a result of the complex Quark-Gluon dynamics, lead to a negative value for its squared charge radius." End quote. What is important to understand is that the quotation taken from Sparveris is not unique or specific to the author. It is the position taken by the standard model of particle physics. His statement is particle physics doctrine as it stands today. Thus, according to the standard model of particle physics, the only way to express the mean squared charge radius of a neutron is by utilising a negative value. What this implies is that the natural form of neutron size we derive should not be possible due to complex Quark-Gluon dynamics. Yet, it is possible, and we clearly show it. We have demonstrated how the concept of 0-point field equilibrium radius compensates for an inconvenient limitation in the standard model of particle physics. This is not a trivial achievement and should not be flippantly dismissed. Therefore, we can confidently claim that we have disproven the premise of complex Quark-Gluon dynamics in relation to the size of the neutron. We are not claiming that complex Quark-Gluon dynamics do not exist. We are claiming that the premise of complex Quark-Gluon dynamics is irrelevant with respect to the size of the neutron. Let's now take a look at our exact analytical solution. The derivation sequence for the zero-point field equilibrium radius of the proton and neutron is astonishingly simple once the significance of Compton frequencies is realised. When we evaluate the ratio of particle Compton frequency squared to the electron Compton frequency, we find that they are equal to the second simplified harmonic cutoff frequency as shown. Once this relationship has been realised, a string of simple substitutions yields the exact analytical solution for the zero-point field equilibrium radius of the proton and neutron, appearing at the bottom of the screen as r sub pi and r sub nu respectively. These exact analytical solutions may seem innocuous, but nothing could be farther from the truth. The fact that the form of each solution is identical is extremely important and very telling. Given that we have established the experimental validity of both solutions, it is a very powerful statement that they have the same form. This is exactly what we would expect if we were discovering these particles for the first time, due to the similarity of their masses. The standard model of particle physics does not and cannot achieve this. When utilising conventional methods, the neutron mean squared charge radius is a negative quantity, whilst the root mean squared charge radius of the proton is a positive quantity. This disparity is a significant indicator of a problem within the standard model of particle physics, requiring correction. We know for a fact that a problem exists because we have derived a solution without the same disparity. Let's now summarise what we have learned. The lessons learned in this episode are as follows. 1. The standard model of particle physics asserts that due to complex Quark-Gluon dynamics, the neutron mean squared charge radius takes a negative value. 2. According to the standard model of particle physics, a natural positive valued dimension like the proton root mean squared charge radius is impossible with respect to the neutron mean squared charge radius. If it were possible, then the standard model of particle physics would utilise natural dimensions, that is, positive dimensions, not negative dimensions, to communicate the neutron mean squared charge radius. 3. Storti and Desiato derived experimentally verified exact analytical solutions for the proton root mean squared charge radius and the neutron mean squared charge radius. Please refer to episode 5 and the stated research article via the link shown for more information. 4. The bottom line. Storti and Desiato's exact analytical solutions disprove the standard model of particle physics premise that complex Quark-Gluon dynamics necessarily leads to a negative value for the neutron's mean squared charge radius, as published by Kopecky in 1995, Kamenov in 2002 and Sparveris in 2021. In other words, the Quark-Gluon premise is just speculative guesswork. The standard model of particle physics has no idea if its premise is actually correct or not.